In episode 1, we covered why hybrid search exists, the two failure modes of pure semantic search, BM25 mechanics, HNSW, and RRF fusion. If you have not seen that episode, the link is in the description below. It's worked 18 minutes before this one. Today we build it. By end of this video, you will have working Qdrant collection with hybrid search over 500 product records, dense semantic vectors via sentence transformers, sparse BM25 vectors via FastEmbed combined in a single prefetch request using Qdrant's query API with RRF fusion. I'm going to show you the specific settings that matter in production, not just the defaults, because some of Qdrant's defaults are prototype defaults, and I'm going to tell you which ones to change before you go production. The demo at the end, a side-by-side query, iPhone 15 Pro Max 256GB, dense only versus hybrid. I will show you what each returns at rank 1, and we will put a precision number on the improvement. Let's build it. Before we write any line of code, let me show you what we are actually building. Here is the architecture of what we are building today. Two sides, indexing and query. On the indexing side, we take a document, in our case product record with the name, description and metadata, and we generate two representations. First, a dense embedding from a sentence transformers, all mini LM L6 V2, a 384 dimensional float vector capturing semantic meaning. Second, a sparse BM25 vector from FastEmbed, a high dimensional sparse vector capturing lexical weights. We upsert both into a single Qdrant point with payload metadata. On the query side, a user sends a query string. We generate both representations of the query, dense and sparse, and send them to the Qdrant in a single prefetch request. Qdrant runs both searches in parallel on the server, fuses the candidate listing using RRF, and returns the top key results with payloads. One collection, two vector spaces, one request. That is the architecture. The key thing to notice, we are not making two separate API calls and doing fusion in our application. The Prefetch API pushes the fusion to the Qdrant server. This matters for latency. Two sequential requests are slower than one parallel request, and application-side fusion is slower than server-side fusion. Let us start with collection creation and the settings that matter. Here is the collection creation code. I am going to walk through every parameter here. The collection has two named vector spaces, dense and sparse. This is Qdrant's multi-vector architecture. Each point can carry multiple named vectors, and you can search each independently in a combination. The dense vector, 384 dimensions, cosine distance, all mini LM L6 V2 produce normalized embeddings. So cosine distance is correct. If you use a model that produces non-normalized embeddings, like text embedding 3 large for example, use dot product instead. The sparse vector, no dimension size required, because sparse vectors are variable length. The onDisk equals to false setting keeps sparse index in memory. This is the production settings for low latency retrieval. OnDisk sparse indices are for very large collections where memory is constrained. One important note, OnDisk equals false for sparse index is not the default in older Qdrant versions. Check your version. Sub 10 millisecond sparse retrieval requires the index to be in memory. Collection is created. Now let us index the documents. The most common question about Qdrant hybrid search is, do I need Elasticsearch or Solr to get BM25? No, Qdrant ships with FastEmbed, a native Python library that generates sparse BM25 vectors entirely in process. No external services, no Elastic cluster. How to set it up is on the screen. In the left hand side with code, the Qdrant BM25 model is FastEmbed's BM25 implementation. It tokenizes the text, and computes TF-IDF weights exactly as I described in the episode 1. The output is a sparse vector as a Python object with two arrays. Indices means the vocabulary dimensions that have non-zero values, and values means the BM25 weights at those indices. One thing worth nothing. FastEmbed's BM25 computes IDF based on the documents you have embedded locally. For small test datasets, IDF weights may not be representative. In production, you want Qdrant server-side IDF modifier, which recalculates IDF based on full collection as it grows. I will show how you to enable in a moment. The dense model is also FastEmbed compatible. For example, it runs inference locally via on an NX. No GPU required. True, if you have one, it will be faster. Let's go to the Visual Studio, VS Code. In the setup, there is an index documents py, there is a dense and sparse model here. Let's go inside the setup folder. Before to do that, first we need to install the requirements. Right, everything installed, and we upgrade our pip to. Then after we will go to the setup folder and index document py preview sparse. It's loading the embedded models. Okay, now the sparse is installed. The preview is already worked, and the crash happened later when abstracting the Qdrant because Qdrant isn't running on the localhost. Let's use the Docker and install the Docker image of the Qdrant. Qdrant is up and running. Then we need to go to in another terminal. Here we are. Let's go inside setup and run the create collection py. Now products has been created and payload indexed on category. Let's index documents with preview sparse. Now we have the indices, values, and look, for 500 products, now it's upserting batch by batch. Done. 500 products indexed. That's it. Models are ready and 5 product records indexed. Here is the full indexing loop. A few things to notice. I am concatenating name and description into a single text, as you can see it here, before embedding, of course. This is intentional. Both the dense and sparse models embedded the same text. The representations are of the same content, just through different lenses. I am batching upserts at 64 records. Qdrant handles large batches well, but network overhead per request is real. Batching is the production pattern. The payload contains the full product record, name, description, category, and price, and CQ. This payload is returned with search results and it's also filterable. We will use that in the query step. So 500 records index, let us query, and this is where Prefetch API comes in. This is the query API introduced in Qdrant 1.10.0. Let me walk through the structure. The prefetch list contains 2 subqueries, one dense, one sparse. Each runs independently and returns 20 candidates. The using parameter which vector space to search, the limit is 20. This is the candidate list size before fusion. I recommend 20 to 50 for most use cases. Larger gives the fusion algorithm more material to work with at small latency costs. The query parameter is fusion query, fusion equals to RRF. This tells Qdrant to apply reciprocal rank fusion to the 2 candidate lists, but subqueries run in parallel on the server. The fusion happens server side, one network round trip. The final limit top key is the result counter after fusion. You fetch 20 candidates per path, fuse them, return the top 10. This is the version 1.10 and above only. Check your Qdrant version before deploying. Since we already started in Docker, so we can also play around with the localhost 6333. Let's go back to the code. Let's go to the search folder and write the hybrid request of iPhone Pro Max. Let's copy this payload and let's go back to dashboard, products, under collections and points. Here we are. /query. Yep, here in the console we paste this collection products and let's run it. Look at that. Now we have some points like iPhone Pro Max. Subquery 1, dense ENN top 25, sparse BM25 top 20, both run in parallel on server. RRF fuses the candidates, final limit returns top K. Here's the result. The perfect pattern gives us performance. Now let me show you payload-aware filtering, the right way to filter, not post filter. In episode 1, I mentioned Qdrant is graph filtering. The HNSW graph traversal stays within nodes that satisfy the filter. Rather than filtering results after search, here is how you use it in a hybrid query, this code. The filter is applied at the query level, not as post-processing step. Qdrant's HNSW graph traversal honors this filtering line. It only visits nodes in the graph that satisfy the category condition. If you have a payload index on the category field, this is as fast as unfiltered search. Look at this client create a payload index. This is one-time operation. After that, filtered hybrid queries run the same speed as unfiltered ones. If we go back our code, we can also run this noise cancelling wireless headphones top key 5 search. Let's take this JSON output in the clipboard and go back to the console and paste it here and run this. As you can see, the results is instant. So this shows the same prefetch from the same prefetch flow plus top level filtering. Look, Apple AirPods, Bose Quiet Comfort, Sony VH, and others. Again, a Bose Quiet Comfort 45. So one more production settings before the demo, another demo. Server-side IDF. Fast embedded local BM25 computes IDF based on the document you index in your application. For a static dataset, this is fine. For a collection that grows over time, documents are added, categories change, new terminology appears. The IDF weights become stale. Qdrant supports a server-side IDF modifier. The server recalculates IDF based on the current collection state whenever the collection changes. To enable it, you can use this code, sparse vector params. The modifier is IDF. Line is all it takes. Qdrant handles the IDF calculation and update automatically. Your application does not need to re-embed or re-index when the collection grows. For a demo dataset of 500 products, this will not make visible difference. For a production collection that grows month over month, this setting that keeps your BM25 rankings accurate as the collection evolves. Enough setup. Let me run the comparison. Here is the moment the whole episode has been building toward. I have 500 product records indexed. I am going to run same query through 2 retrieval methods and show what comes back. The query iPhone 15 Pro Max 256 GB. Then the search will result top 5 result. Okay, as you can see on the left hand side. The correct answer 256 GB is rank 2. The wrong answer 128 GB is at rank 1. This is exactly the failure mode I described in the episode 1. The semantic model cannot distinguish storage capacities. On the other hand, in the right hand side, we have the hybrid search. Look at the top 5 result. The correct answer is 256 GB is at rank 1. The BM25 sparse vector matched 256 GB exactly and ranked the correct product first in the sparse retrieval list. RRF Fusion elevated it to the top of the combined ranking. This is precision 1. Dense gets 0%. Hybrid gets 100% on this query. Across all 10 SQ style test queries in comparison script, dense only precision is 40%. Hybrid precision is 90%. That is the 30% improvement you see cited in the Qdrant documentation. It is real, reproducible on exact identifier queries. Here in the search folder, look, Python dense only py. Oh, my bad, I fixed my error. Now Python dense only py. This is the dense only result. Let's go for the hybrid. Now we get the hybrid. Now comparison. Yes, this output is valid technically, but it does not support the dense fails hybrid wins narrative. Why this is happening? Because comparison py uses the correct name substring matching, which it is lenient. So this dataset likely repeated similar product names, so top results can look identical now. And query text exactly matches index text strongly, so dense also scores perfectly in this case. But if we run the find showcase query py, we have now top showcase queries. Hybrid improves rank versus dense. It those ones. Oh, sorry. Let's run the dense only. For example, here 30. Now we run the comparison. As you can see, the hybrid is better. Now print ID and SQs, not only the name. So duplicates are clear now. So comparison py now evaluates by exact ID result from the corrected SKU, not fuzzy name contains. So yeah, that proves it. This hybrid approach is much more good, much more better than dense only approach. Before we wrap, let me call out the production settings are changed from defaults. 4 settings that are not defaults but should be in the production. First, sparse index on disk. The default in older Qdrant version was on this sparse indexing. Set on disk false in sparse index params. In memory sparse index is difference between 8 milliseconds and 40 milliseconds P95 on sparse retrieval. Second, IDF modifier. Enable modifier IDF on sparse vector config. Without it, IDF weights are stale for growing collections. Third, payload index on every field you filter by. Do not filter on a field without payload index. Qdrant will do a full scan, not an index lookup. Fourth, candidate list size in Prefetch. The default limit is 10 per Prefetch lag. For product search, use 20 to 50. RRF needs enough candidates from each list to do meaningful fusion. If the correct document is ranked 15th in the sparse list, but you only fetch 10 candidates, it is visible to Fusion step. These 4 things are what the difference between a prototype that passes your tests and a system that's holed up in production. Let me wrap up and show you what's in the GitHub repo. The GitHub repo is the Qdrant Hybrid Search Lab, branch episode 2 Hybrid Search. Here is what you get, is here. Clone this repo, spin up the Qdrant with Docker, one command in the README, run the setup scripts in order, then run comparison py. You will see the precision difference yourself with your own numbers. In episode 3, we wrap this in a fast API service, add a cross encoder re-ranker as a second stage, and quantization to cut memory by 4x, and benchmark the full pipeline against Dan's only 10 labeled queries. If you found this useful, please like and subscribe. Link of the GitHub repo is below. Also, the episode 1's link is in the below, and the link of the Qdrant documentations are all in the description below. Thank you. See you in the next episode.